Hey class, Mr. Bean here. This is some procedure and information about how to complete Lab 34 just in case you cannot make it to class. Anyways, so it's going to be a virtual lab. And in principle, we're going to replicate the Cavendish experiment. Now, on the lab sheet itself here, there's some information about what Cavendish did and what Newton did, and so on and so forth. And so what this lab is called the value of G. Okay, how did they get the value of G? Well, he did a Cavendish. This is the Cavendish experiment here, which explains how they did it, and this is how they calculate the value of big G. So this is called the gravitational constant, and it equals big G. So when we see the equation, F, the gravitational force, is equal to big G, right? We'll say M1, here's M2, all this divided by R squared. This is the gravitational constant here. It has a value, accepted value is 6.67259 times 10 to the minus 11 newtons meters squared kilograms squared. All right, that should be a square here. I got to fix that. Okay, hit pause real quick here. Okay, all right. So, so we're going to be using this virtual lab over here, which is going to, in principle, replicate the Cavendish experiment over here. All right. So now I'll kind of show you how we're going to do this. This is the theory behind it here. And what's going to happen is that we're going to hold mass 1 constant and hold R and mass 1 constant, and we're going to adjust mass number 2. Okay, so here we have a table here where we'll have different values for mass 2 and the force. All right, so first thing we want to do here is we want to set the radius. So I'm going to go ahead and move this over to here and maybe, okay, for maybe we'll use 5 meters. So I'm going to go up here and measure the radius difference. Okay, so let's say it's 5 meters here. And my mass 1 is going to be 100 kilograms, let's say. So over here, I'm going to say that mass 1 is what, 100, we have 100 kilograms. So you don't have to use this. You can use whatever you want to. Mass 2, the radius is going to be 5 meters. Okay. All right, so I'm going to reduce mass number 1 to, I don't know, maybe 70. Okay. All right, so mass 2 is going to be 70 here. And here is the force. Now, here's the force up here, and here it gives us a value. Do you want decimal value? Do we want scientific notation, or do you want to hide it? Let's go ahead and just do scientific notation. Now, if I do that, I got to be careful here, okay, because I'm going to be using an online graphing program, right? So it's 1.87 times 10 to the minus 8. So when I write it in here, I'm going to do 1.87 like so. 1.87. I'm going to write E. Okay, it's E minus 8. Okay, so we'll go ahead and do this here, right? And then I'll do a couple more. I'm going to do a couple more masses and a couple more forces. Okay, then I'm going to use the online graphing calculator, Quick Graph. Okay, Quick Graph tool, and let's go ahead and see what that looks like here. The Quick Graph tool is here, and we'll use 4.0. So we're going to transpose the data over to here and make a graph. Okay. Now, the graph in principle should look like this. Here's force here, right? This is force, and this is going to be M2. Okay. The graph should have this feature like this. Okay. So what does that mean here? Okay. So let's suppose here I have F is equal to, here's big G here, right? Here's mass 1. I'm going to say over R squared times M2. Okay, so see this part right here? Okay, so let's maybe call it, we'll call it A. So this is A, which is this basically, so here, the slope here, this is what A is. A is the slope of this line right here. So A is going to equal big G, right? Here's m1 all over r squared. So we have our values over here. We should be able to solve for big G. And the question is, what is big G? And hopefully your answer here is to within 10% of this over here. All right. Okay. Hit pause real quick. All right. So you're going to calculate. So from here, you're from the graph, from the quick graph here, I want you to rewrite the graph here. I'll make sure you label this here with the appropriate units here, label this, and I want a title. Okay, and slope from the graph and show your calculation of G and then do your percent error. Okay, so that's going to be part A. All right, part B, you'll be using the same gravity force lab here, except this time you're going to hold mass 1 and mass 2 constant, and you'll be adjusting R. Okay, you're going to adjust R. Okay, so set mass 1 and mass 2, and then I would just adjust R. For example, go with 2, 3, 4, 5, 6, so on and so forth. Okay, fill this box in here of R and force here, and construct a graph again. Okay, now what you're going to do is this. Okay, so here's a theory here. Let's see, take a quick look here. Okay. All right. So here's the theory here. So if I was to plot force here as a function of the radius, just the radius itself, okay, I want to get what's called the inverse square law. Okay. So that means here it is here. It's going to come down like this. It's going to be inverse square. Okay. So it should look something kind of like this. It's what's called inverse square. Okay. That means that this would be 1 here. This is 2. This is 3. This is 4. And this here is okay. Yeah. So it should look something kind of like this. This is inverse square. Then we also want to be able to find G. Okay. How can we find G from this? Okay. So let's take a look at the equation here. The next part you're going to do is this. So here's our big G right here, right? You're going to hold M1 and M2 are going to be held constant. It's going to be here like this. And we're going to times it by 1 over r squared. Okay, I mean, that's Newton's law right here, universal law. Now, if I was to plot F over here, and I was to do 1 over r squared here, okay, I should get a straight line. Okay, and just like before, this is the slope, right? It should be a straight line here, and the slope, whatever the slope is going to equal big G m1 and m2. So once I find the slope, I can very quickly figure out what G is going to be. Okay, so that's going to be part B here. Here's the graph for R versus R and force. Here's the graph here, and this is 1 over r squared times f. Okay, so we want to plot f versus 1 over r squared. All right, construct a graph here, put it over here, and we're good to go. Calculate what G is. So I think, yeah, there we go. All right. All right, then finally, you want maybe describe a procedure on how to do that. Okay. All right, part C, the Jupiter project. Okay, so here we have thing. We have some data here on Jupiter, and these are the 4 of Jupiter's moons, Galilean moons: Callisto, Ganymede, Europa, and Io. This is their distance from Jupiter. This is the orbital period, and this is the mass of Jupiter. Okay, so what you need to do here is we want to figure out what is the mass of Jupiter based on the period data from NASA. Okay, so we want to figure out what is the mass of Jupiter. Okay, the mass of Jupiter. So we want to say mass, right? Mass of Jupiter. Okay, mass of Jupiter. Okay, so here's how we do this. Okay, so here we have, here's Jupiter. Let me use, get red here. And here's the red spot on Jupiter right here. And it's got some bands going this way. There's a red spot. Okay, and here's maybe one of the moons here. Okay, it's going like this. Okay, and this distance here is going to be r. So I think that's what R is, distance from Jupiter. So we'll use this information here. Now, be careful now. This is kilometers, so it's times 10 to the 3 kilometers. This has to be in meters. Okay, so when we transpose this information to over here, it's got to be in meters. Okay, now these are in orbital days. This got to be in seconds. Okay, so to help you out here, I can say that 1 day, right, is equal to 86,400 seconds to help you with the conversion here. Okay, so make sure these are all in these meters and these are all in seconds. Okay, now, so let's take a look at what we're going to do here. So here's this project sheet here. This is this. I have a link here to this Google Sheets here that I made. Once you have R here and T here, I want you to take this information and just plug it in here, here. It should calculate mass of Jupiter for you just like that. But you have to get this part done first. Okay. Now the theory. So here's the theory here. Okay. So gravity is keeping this in nearly circular orbit. Okay. So that means that we have here the force of gravity is supplying the centripetal force. Okay, so the force of gravity is going to be big G. Okay, here's the mass of Jupiter, and little m will be the mass of the moons there, divided by r squared, like so, right? Equals, that's the mass of the thing going around in a circle, and here is v squared over r. Okay, so this mass here represents the mass of the moon going around in a circle. Now look closely. This is gone, that's gone, this is gone, as well as that. So what's left is that I have big G, the mass of Jupiter here, divided by R, right, equals V squared. Okay. Now recall, V, right, is 2 pi R, right, over T, right? So V squared, right, be careful now, it's going to be 4 pi squared R squared, right? All this divided by T squared. So okay, so now substitute this into here, and what we get here is big G, right? Here's the mass of Jupiter here divided by R, which equals, now I gotta be careful over here, we're gonna put in here 4 pi squared, right? R squared all over T squared. So I need to solve for the mass of Jupiter. So the mass of Jupiter, right, is going to equal, here we go, 4 pi squared, right, r cubed, all this over big G over T squared. So this is a formula that we are going to use, but I was nice enough to calculate, already program it into the spreadsheet. So all you need to do is make sure we have this converted from kilometers to meters here. Be careful now. You got to watch out for this, right? So you add, so, this is kilometers. So that means that you have to make this times 10 to the 6 if you want to. Times 10 to the 6. Okay. Just be careful. And make sure you convert this to seconds. All your answers should be the same over here. All right. That is it on this lab here. Okay, and I'll go ahead and pause here, and I'll go ahead and that is it. Any questions, just make sure you email me, and away we go.